A linear program is a special type of an optimization problem, and an optimization problem is a linear program if both the objective and the constraints are linear. So we should have a linear objective function, so the thing that should be maximized or minimized should be linear, and the constraints should also be linear equalities or linear inequalities. We also talk about the dimension of a problem, and that's the number of the decision variables. So for now we will consider a linear program, an LP with two variables. But if you consider more practically realistic problems, then you can easily have hundreds or thousands of variables. If you would like to formulate a linear program, then the first thing is that we organize everything that we have. Then first in words the question is what is the objective, and then corresponding to that we choose the decision variables. So basically what are we choosing? Then we write down the objective function and we also write down the constraints. As an example, let's consider Geppetto's wood carving. So Geppetto manufactures soldiers and trains, and the aim is to maximize profit. We have information available, so the soldiers can be sold for $27 and they use $10 of material and $14 of labor. Trains can be sold for $21 and they use $9 of material and $10 of labor. For each toy we need carpentry and painting as the two types of labor. The soldiers require 1 hour of carpentry and 2 hours of painting, and trains require 1 hour of both. And then there is limited capacity, so Geppetto only has 80 carpentry hours available and also only 100 painting hours available. And we can also sell at most 40 soldiers per week. So it doesn't make sense to produce more than 40 soldiers. So we can organize the data. So what do we have? For both the soldiers and the trains we have costs and we have revenues. So the cost for each soldier is 24, revenue is 27. We can also organize the labor time that is needed. So for carpentry it's 1 and 1. And we have 80 hours available. For painting it's 2 and 1 and we have 100 hours available, and there is a maximum demand of 40 soldiers. The objective is to maximize the profit, and we would like to do that by determining the optimal number of soldiers and the optimal number of trains. So the question is how many soldiers to produce and how many trains to produce. So that is how we are going to define the decision variables. So we are going to use the decision variable for the number of soldiers to produce. Because soldiers starts with an S, we can for instance use XS and then XT for the number of trains to produce. Of course you can also use X1 or X2, but it's important to define the decision variables in words. Then the objective function. So we are going to maximize profit, and then the question is how does the profit depend on the values of the decision variables XS and XT. For each soldier that we produce we have a certain profit. For each soldier that profit is 3 because the revenue is 27. Total cost for each soldier is 24. So 3 is the profit per soldier. We multiply that by the number of soldiers, so then we have the profits that we get from producing the soldiers. The same idea for the trains, it's 2 times XT. And if we add those two, then we have the total profits. So 3XS plus 2XT is the total profit. That's the thing that we would like to maximize. So our objective is maximize in front. You can give the objective function a name, so we can call it Z. It's 3 times XS plus 2 times XT. That's the objective. Then the constraints. So in this case we have 80 hours of carpentry available. How much carpentry do we use for a given solution? If we produce a soldier, we need 1 hour of carpentry, and also for a train we also need 1 hour of carpentry. So the amount of carpentry hours that we use is just the sum of XS and XT, and that sum should be smaller than or equal to 80. That's the first constraint. Second constraint is for painting hours, so 100 available, but for each soldier we need 2 painting hours. So that means that 2 multiplied by the number of soldiers that we produce plus 1 times the number of trains that we produce. That's the number of painting hours that we need, and that cannot exceed 100. So this is the second constraint that corresponds to the limited number of painting hours available. And we can sell at most 40 soldiers. So we just have that XS should be smaller than or equal to 40. So that is this constraint. If we now solve this problem, it can happen that we get negative values for the decision variables. In this case, maybe for one of the two decision variables. That can of course not happen because we cannot produce negative quantities. So we should always also add the non-negativity constraints. So here we have XS and XT are both greater than or equal to 0. And then we have the complete linear program. So we have, we always start with the definition of the decision variables. Very important not to forget this, because if you don't define the interpretation of the decision variables, the entire model cannot be interpreted. So this is how the decision variables will be defined. We are going to maximize the objective function, and then subject to these constraints and also subject to our non-negativity constraints. Then a little bit about terminology. So we have coefficients, and we have two types of coefficients. So we have the objective coefficients, are the numbers 3 and 2 over here. And we also have the constraint coefficients, and those are the numbers over here. The numbers in front of the decision variables. So the 2, the 1 here, the 1 here, the 1 here, the 1 here, and the 0 here. Those are the constraint coefficients. And then we also have the right-hand sides. The right-hand sides are the numbers over here. And combined, so if we have the coefficients and the right-hand sides together, then that entire set of numbers is called the parameters of our problem. Then the function that we are maximizing or minimizing is called the objective function. So that was the function for Z. And then the first set of constraints are called functional constraints. And then we have the non-negativity constraints. So the set of constraints can be split into two parts: functional constraints and non-negativity constraints. We also talk about solutions, and important is that the solution is any specification for the decision variables. So any values does not need to be a feasible solution, and that's because there is a distinction between feasible solutions and infeasible solutions. So if a solution satisfies all constraints, then it's feasible. If a solution does not satisfy one of the constraints, then it's an infeasible solution. So here as an example, if you specify, for instance, XS is equal to 40 and XT is equal to 40, this is a solution because it's a specification of the decision variables, but it's an infeasible solution. And it's an infeasible solution because if we plug in 40 for XS and also 40 for XT, then this left-hand side will be 120, but it should be smaller than or equal to 100. So that's why this is an infeasible solution. If we are going to search for the optimum solution, then that's the best feasible solution. So the optimum solution is the best solution among the feasible solutions.